go to her and ask her directly question. This is monitored by Flavine and Maria, and we are going to the next.
Now let's go because we're running out of time. So we have Peter Steele from Airbus. He's actually he has worked on the clean-hand harpoon and also on the Sunrise active debris removal. So whenever you're ready, Peter, over to you. We're waiting for your talk. Thank you.
Thanks, guys. Thank you for inviting me today. I was at Cranfield about 4 years ago on the Space Engineering Masters. So I actually was involved in setting up the very first kind of Cranfield Space Policy Day, and I'm very pleased to see how it's kind of grown way bigger than it was back when I was there. So well done. So today I'm going to follow on from Zoe's talk by talking about active debris removal using harpoons. So a different method that we've been working on at Airbus. Some quick background on me. So after I was at Cranfield 4 years ago, I've been working at Airbus ever since in the Future Programs department, so same department as Zoe was. And I've been working mostly on space debris missions, both using harpoons and also robotic arms. So kind of both angles of the problem. So go to the next slide, please. So yeah, we'll start off by a brief introduction of space debris, which I can kind of go through a bit quickly because Zoe has already given you a good overview of the space debris problem. But I want to kind of convince you that there are other ways, and there are multiple ways of getting down space debris, and I think a lot of them have different roles to play that can all be useful. And then I'm going to show you the two harpoons that Airbus has developed. Firstly, the remove debris harpoon, which is a small harpoon that's been tested in orbit. So it's a nice proof of concept that it actually can work, but it's quite a small harpoon. And then we've got the clean space harpoon, which is much bigger, and that's sized for taking down the very biggest space debris targets, the kind of targets that we had to remove from space to have a big impact on space debris. And that's gone through ground testing at the moment. So next slide, please. So a lot of this I'll whiz through fairly quickly because Zoe covered it so well. There's over 25,000 tracked objects in Earth orbit, and most of those will be over about 10 centimeters in size, big enough to be tracked from the ground by radar. But there are a lot of smaller ones as well that we theorize exist. We know from our modeling and from ground tests on Earth that collisions in space and these kind of things and our records, we know those fragments are up there, but we can't track them, and therefore we can't avoid them when they're coming our way. Most of these stay up in space for decades and decades, sometimes hundreds of years if they're high enough, before the residual atmosphere causes enough drag to bring them down into a re-entry orbit. And the graph on the upper right is from ESA's sort of debris. It's almost like a debris weather forecast that they produce every year, showing the state of the low Earth orbit. And you can see the numbers going steadily up and up and up. And what I just want to draw your attention to is the two steps in 2007-8 and 2009-10. And these are just from two individual events. There's the Iridium Cosmos event, which Zoe mentioned, the one functioning satellite and the one defunct satellite that smashed into each other, and both of them just exploded into a big pile of fragments, more than the number that you see the jump by, because of course we can't track all of them. And secondly, in 2007, there was a Chinese anti-satellite missile test. They actually blew up one of their own defunct satellites with a missile in low Earth orbit that's high enough that those fragments will stay up there for a long time. And you can see that also caused a very big jump. So these are just 3 satellites that have exploded and caused this huge increase in the number of fragments. So one event can have a very big impact, and these weren't even these were kind of medium-sized satellites. So the larger ones will potentially almost double the number of fragments in one go if something hits them the wrong way. There's also the frequent near misses and the minor events that we have. Zoe mentioned the ISS being struck by debris. There's a little close-up photo of you. They only found it when they went out on a spacewalk. They kind of looked at the arm and they're like, oh, something's gone through here. It was never a tracked piece of debris, too small for that. And luckily it hit the Canadarm and not the main capsule, otherwise it could have been quite bad. One key point that is important is the things that are dangerous to spacecraft, manned spacecraft and operational spacecraft are tracked debris, which we can avoid if the satellite is functioning, but also untracked debris and the smaller pieces which you don't know where they're coming. But if you have two large satellites that are tracked, that are dead, or two large pieces of debris, the chances of them hitting each other is entirely probabilistic. You can't do anything to avoid two objects hitting each other if you can't control either of them, and that creates loads more fragments. A lot of them will be uncontrolled, well, all of them will be uncontrolled, but a lot of them will be small enough that you can't track them. So the situation can very quickly get to the point where it becomes a runaway effect. Next slide, please. So how do we solve this? Active debris removal can provide a solution. So on the right, you see this is a graph showing the 30 largest European objects in space, and by debris risk index. So this is just a measure of how likely they are to collide and make the space debris problem worse. And you can see that even between object number 1 and object number 30, there is a factor of around 30 in the risk. So removing the very top target would be equivalent to removing 30 of a target that's still even very bad. So we've done some modeling on this, and we can actually show that if you remove a couple of the biggest objects every few years, then it has a very big effect on the long-term debris population. The fragments that are there in space start to fall down into re-entry orbits faster than collisions would create them. And it's just a couple of big objects a year. Removing those can be achieving that. So the biggest impact is by removing the largest debris objects is the important point. And there's lots of ways you can do that. The basic way, what you need to do is rendezvous with your target and influence its orbit so that it comes down. Ideally, you want this one to be a controlled re-entry, so you choose where it comes down, because something this large won't entirely burn up in the atmosphere, and you don't want it hitting anywhere remotely near a populated city, for example. So you can capture and remove it directly. You can try and capture it with a robotic arm or magnetic capture, much like Astroscale is looking at. We're also looking at similar concepts in Airbus, or you could use a net to kind of wrap around it, and then a tether to kind of drag it back to where you want it. Or you could attach that tether to a harpoon and spear the debris object and then kind of drag it and detumble it. Or there's more exotic ways that you can do it without kind of dragging it back directly. You could attach some kind of a drag sail, for example, to the satellite and then leave it, and just basically increase the drag coefficient, which allows it to deorbit naturally much faster. For the big objects, that's less of an option because they have so much momentum that the drag, it would simply take too long. You'd have to attach such a huge drag sail that it's not really efficient. There's also other exotic ideas, attaching weights on strings to try and steal more of its angular momentum around its orbit and slowly bring it down that way. There's or firing lasers at it from the ground to try and influence its trajectory without by kind of photon pressure. There's lots of more exotic ideas, but what we're going to focus on today is the direct approaches. Next slide, please. So what tool is best to use? It's quite a varied question. There's a lot of debate going on, really. So if you want to use robotic or magnetic capture, you go up there with a satellite and some kind of interface or robotic arm to grab a tumbling target. The rendezvous dynamics of that can be very difficult, especially for a large target. You have to be nipping around with a very agile chaser satellite, dodging the flying appendages, the large radiators or solar arrays that these kind of large objects have. in order to get to a suitable point to grapple onto or to attach onto. And you have to remember, most of these targets, all of the big debris ones at least, were not designed to be captured after they're launched. They didn't include a special point to grapple onto, so you're going to have to find one. And make sure in advance before you launch that the point you choose will be able to hold the loads that you're going to apply to it to detumble it and drag it back. So for small targets where you can reach kind of around the whole target with the robotic arm, you can see in the upper image there, that small target on the top right, even if it's spinning, the robotic arm could follow the attachment point while the chaser satellite remains stationary. So that would be a very good target for robotic removal. Once you're attached, of course, it becomes very efficient because all you need to do is stiffen that connection and then detumble it using the thrusters and tow it back to where you want it to be. There's also funding benefits because robotic arms can be used for non-debris applications in space. You can build things, you can manipulate things to assist astronauts. There's a lot of funding streams, so that's quite attractive. Other alternatives, the nets. This isn't too useful for large objects either, simply because you'd have to have such an enormous net to wrap around the surface area of a target. So for smaller objects, nets can be very useful. You don't need to have a special attachment point that can withstand your load. All you need to do is wrap it up in your net and then drag on your tether. The tether dynamics themselves, it's a bit difficult, bit risky to have a large mass on the end of a string and try and detumble that and tow it. You need to be careful, otherwise in space, if you ever have a force moving towards your spacecraft, have like if your tension in the rope drops to zero, you're now running the risk of your two objects on the string colliding and making more debris. So that's quite a big risk that you need to design very carefully to avoid with tether dynamics. It's also quite difficult to test on ground because if you throw a net in space, it'll always expand until it reaches the limits of its expansion, and then it'll start bouncing back again. On Earth, though, there's no way you can throw a net that won't be affected by gravity because it's a 2D object in its simplest form. So, and gravity acts in one of the three dimensions you have. So you're always going to be affected by if you throw a net, it's always going to change behavior on ground relative to in space. So you have to do it in either free fall in the special planes that do a 0G, or you have to do it in a drop tower or something like that. And that again introduces big size constraints. Then we've got harpoons. There's the risk of damaging a target. If you hit it with a harpoon in the wrong place, you could bounce off, you could break bits off, you could make the problem worse effectively. But if you can capture it, you can then drag it back, and you've still got the teledynamics problems. But harpoons are also much easier to test on ground because you can cancel out the gravity vector by just firing either upwards or downwards, and then the velocity of the harpoon changes, but you can account for that in other ways. The actual dynamics of the harpoon only change in respect to how fast it's going, and you can control for that. So they're easy to test on ground. If you have a very large, well-known target, like the ones we talked about, they're mostly upper stage rocket bodies and very large dead satellites. Harpoons are quite attractive because you have the designs for those targets. You can find a panel or a place on that target that will be quite large, that will be suitable to shoot with a harpoon without risking damaging anything. And for large targets, those do exist. And so for the very largest targets, at least, harpoons are quite attractive. The next slide, please. I think we have a video here of this is a net, just the first net capture in space of an object. What happened is they released a CubeSat from a mission called Remove Debris, which is the one also had a harpoon demonstrator on it. So they released this little CubeSat, and then it spins up, and then they fired the net at it. And you can see there goes the net, and it expands. And then the edge of it just catches it and it wraps it up quite efficiently. So this net didn't have a tether attached to it, so they only tested the net capture They didn't test detumbling using the tether, but it shows that it can work in space on small objects at least. So the CubeSat, once it's deployed, its arms started spinning up. It's maybe 40 centimeters across. So yeah, it's possible. For anyone worried about debris there, that test was done in a low enough orbit that everything re-entered quite quickly. Next slide, please. Could I have the next slide, please? I think my screen might have frozen. Are you able to hear me there?
Is everything okay?
Okay, I can't see the screen right now. Are you on a? It should be called Remove Debris Overview.
Yes, and we can actually see 4 pictures: the satellite, one person in a lab, the harpoon, and another satellite.
I think my feed's just frozen, but I can continue still. So the Remove Debris satellite. It was a satellite carrying this net as well as the harpoon, and it was a European Commission funded mission to basically test different debris capture technologies conceptually in space. And the second image there, you can see them actually pushing it out the airlock in the ISS. It was launched directly from the International Space Station. They put it on the end of the Canadarm, and then it just pushed it away gently into orbit. So it was carrying the net, which we've just seen, the harpoon, which we're about to. It held out a small target on the end of a boom and then fired a harpoon at it. It also had vision-based navigation on board, which basically it deployed a CubeSat and then used cameras to characterize its motion, which is very important to be able to characterize your target before you go in and do anything close to it. And then it had a drag tail as well. It deployed an increased area behind it to increase its drag and slow it down. And that's how the spacecraft itself re-entered. The harpoon itself is the lower picture. So this was designed by Airbus Stevenage. It's around 80 grams, so very small. It's suitable for capturing smaller targets, maybe up to a couple of meters across. It was fired at a small aluminium spacecraft structural panel, so the kind of target that you would be firing at on the wall of a satellite in space. And it has deployable barbs which pop out once you've penetrated through the target, so that you can pull on the tether without fear of the harpoon coming out again. If you have the next slide, please, which I would trust that we've gone to. So the harpoon design itself. So the deployer was gas powered. So we had a small gas generator, which is the purple thing in the top of the upper image, and that generated gas which pressurized the charge chamber, and you can see a little bolt inside that charge chamber with a notch in it. Once that reaches, or as the charge chamber reaches a certain pressure, that bolt fails and then pushes the piston up, and the harpoon gets pushed out of the barrel. That means that you always fire at pretty much the same speed, because the failure point is controlled by the bolt. The harpoon itself, so it's got the tether attached to it, but that's attached on a sliding mount that starts at the top of the projectile outside the barrel and then slides back down to the rear, and that actually acts to stabilize the flight of the harpoon. If you don't do that, if you attach the tether further forwards, then the jerking of the tether as it unspooled actually destabilizes the harpoon flight. So this is something that we actually got from whaling harpoons. So it's interesting sources for technology sometimes in the space industry. So yeah, as I said, the tip goes through, and then there's an impact plate which pushes down and releases the barbs that are kind of held by little sheaths, and they're sprung loaded, so it's all mechanical. And then you're able to pull back on the tether and capture it and control it. So that was tested successfully in orbit 2 years ago now, and I think there should be a video of that, which I hope you can see. Okay, got my feedback, so you can see it. There we go. So it shot the target, and you can see it did capture it. It knocked it right off the end of the boom, which was expected. But the target is now attached to the spacecraft via the tether. So it was a successful capture, and the concept is proven. The next slide, please. So now the clean space harpoon is much bigger. So having proved the concept with the small harpoon, now we design a harpoon that's big enough to take on the largest targets. And the largest target is Envisat. It's the size of a double-decker bus. And the top image shows us basically choosing where to fire the harpoon. And there's several panels that we found that were actually very large. This, like the panel we chose, is about 1 meter by 1 meter. A little bit more, and it's just a solid honeycomb panel with no units behind it, so you can penetrate cleanly and form an interface there, and it will be strong enough to support the detumbling loads. The aim is basically to produce a harpoon that's capable of getting rid of the very largest bits of debris based on the removed debris design. So you'd rendezvous with it. You'd fire the harpoon from a location around 25 meters away. The reason you have to be that far away is because of you can see the big radiation, the big solar array in the lower image. When they spin around, you need to be far enough away such that they don't hit you. So this is another big problem with capturing large targets. They have huge appendages that wave around and get in the way of you. So being able to sit in a stationary position far away and fire from there is quite advantageous with the harpoon. And then you would null the rotation with the tether and then drag it to a controlled re-entry in the middle of the Pacific Ocean. Next slide, please. So the deployer is an evolution of the removed debris design. We needed still a gas gun, but we needed something that was more throttleable than the simple one-speed removed debris one. So you have a gas supply because you need a lot more power for this one. So it's not a gas generator; it's far too big for that. We still have the central charge chamber with the pin with the notch in it at the bottom. So that acts as the trigger now, not the primary. Not the primary propulsion. So when we reach the critical pressure, the pin breaks and the piston moves up the barrel, and those two side chambers are pressurized beforehand to whatever pressure you like. And when the piston moves up, they can then rush in behind it and accelerate it further down the barrel. Effectively, this means you can choose what velocity your harpoon goes at, which is great not just for firing in space, but also for testing on ground. So you can work out what the ballistic properties of your harpoon are with the target, how fast you need to be going in space to capture the target without going too fast and smashing into it and damaging the interface that you've just created, which you then need to, of course, use for detumbling.
Hi, Peter. So we're running a little bit short on time. Can you hear me? Can you briefly try to finish, and then you can continue in Vostok 2 the presentation? You will be able to share your screen.
No
Thank
problem.
You.
There are 3 more slides, I think, or maybe 4. So the projectile, I'll run through it very quickly. Very similar to the removed debris one we have, but it's much heavier and longer. It has the sliding tether again, and also the barbs that deploy in the same way when the impact plate is struck. We've also got internal electronics to verify that you've captured successfully, and then you can send a signal back to your spacecraft saying it's now safe to pull on the rope. And I'll talk about that more in Vostok 2, but I think we better move on now to the next slide. So testing, we fired vertically, as I said. We had most of the tests done indoors in a very small rig, but we also had to do tests in the larger full range, which meant firing vertically 25 meters up a lift shaft, which was an interesting week. And because we had to overcome 25 meters of vertical flights, we also had to fire a lot faster than we would do in space. So in practice, the projectile had to be designed more for ground testing than in space. That ground testing turned out to be more challenging an environment. Okay, and I think I have one or two more slides. So the test results, there are some fancy videos of how it worked, which I'll probably be showing in Vostok 2 by the sounds of things. But we had reliable target capture with reasonable impact velocity that didn't damage the target, and we can capture targets even up to 45 degrees if if the spacecraft angle if the target's rotating, then that's not a problem for us. The interface that was made is solid and it fixed everything. I can see that I've been
so sorry for this.
Off.
I'm so sorry. I feel so bad, but I really have to cut you because our team here needs a little rest to prepare the next people. So don't worry, as I said, you have the link for the Zoom, so you're going to be able to join Vostok 2 already, and you can continue the talk there. Sorry, and thank you so much for today. We're going to go now for a short break. It's going to be shorter now, but then we will have Professor Helen Atkinson, and we'll go with the space debris panel. Thank you so much. See you soon.
See you soon.